we've already taken a look at continuous optimization. But suppose that in addition to minimizing or maximizing some function, f of input vector x, we have some constraint to satisfy. In other words, we can't just choose any input space. We can't, for instance, pick any x and y in this function because we are somehow limited or bounded. And that limit or boundary is usually placed upon the inputs themselves. So let's say that x and y are the quantities of two types of products that we sell, and f of xy is the corresponding cost from selling these, or from manufacturing, all that process. That's the cost function. Now we want to minimize the cost, but we can't just look at this function. We need to sell 30 units, because you might say, well, if you just have an unconstrained problem, well, then you should sell 0 units of each, because then your cost will be $0. We plug in 0 for x and 0 for y. But we need to sell exactly 30 units, let's suppose. And so the question is, what should x and y be in order to sell 30 units, but at the same time make the minimum possible cost? Now, here is how this actually looks in three-dimensional space graphically. So our function f of xy is this red paraboloid, and our constraint x plus y equals 30 is this blue plane. And where the two touch, where they intersect, which you can see is all along here, pick a different color, is all along that intersection boundary, which if you look at the shape of that looks quite like a parabola. Those are the points that we are allowed to consider. So we have to stay within that green curve so that we satisfy both the constraint and we generate a cost that is on that red surface. So the question is, how do we go about doing this? Well, one way that we might have seen such a problem is we could solve for one of the variables, say y, and then get y equals 30 minus x, and then replace y with 30 minus x. And we get a two-dimensional function, which actually makes sense. The green curve is a two-dimensional function. And then go ahead and optimize that. And that would work here, but that's not typically going to be possible. A lot of times we're going to have way more variables, and it's just not going to make sense. So we're going to approach this with a slightly different method. Now, in general, these constraint optimization problems are formulated in the following way. We have either maximize or minimize some function, f of x. This is often called the objective function. And we have then this subject to phrase, which gives us our constraint or constraints. Okay. Now notice a couple of things here. It's not just one function. It's the g vector of x vector. So basically what we could have is we could have g1 of x equals 0, g2 of x equals 0, dot, 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 all the way down. And we could have as many of these constraints as we want. So that's why we have the vector arrow over the g and over the 0, because notice that, well, we have a bunch of zeros on the right-hand side, and we have a bunch of g functions on the left-hand side, each of which somehow depend upon our input space. Now, just to put this back into a graphical view so you can kind of see the three-dimensional rotation of it, we can actually see where the minimum would be, right? The minimum would actually be at this point here, and that would produce the lowest possible cost. Now, in this case, it would be a negative cost. We know, of course, that producing 0 units would produce the lowest possible cost, but this one has dipped down a little bit. But anyway, that would be the minimum right there. And this x plus y equals 30, notice it's a three-dimensional function. It's a vertical plane. It sits perfectly vertical. It just kind of slices through the xy plane. And also an important thing to notice is that recall that each value of z, if I fix a value of z, say z equals 200, and I plot z equals 200, what that does is it slices through my function, and it produces what's called a contour. And the contour is the circular ring here, which indicates that everywhere along this surface where z equals 200 slices through it, if we were to walk around this ring where the blue and the red meet, we would not be changing our elevation at all. Imagine just kind of like, walking along this surface. And if you were inside of this surface and you were just walking around that circle, you would not be working hard to increase or decrease your elevation. You would be walking uphill or downhill. You would just be walking around in a circle. Now, of course, we could make that higher. We could say go up to 300, and the only thing that changes because of this, the shape of the paraboloid, is that that ring gets a lot larger versus if we go down to, say, z equals 100, same ring, right? Just a lot smaller in radius. So that's going to become important because as we start to think about how to optimize this, we need some facts that are going to help us do this. And I want us to have a little bit of an intuition behind how this works. So the gradient of a function at a point is orthogonal or perpendicular to the level curve at that point. Now, level curve is the same phrase that means contour fixed value of z. So at each fixed value of z, we get one of these circles. Now here I just have a variety of them. I could actually go into our graph here, right? And I could just slice this at many points, and each one of them would just create a circle of different radius. And so here is just a variety of them. And let's just say that I pick a point that happens to be on this red contour right here. Okay, and if we think about what the gradient tells us, the gradient tells us which direction we should move in order to increase our elevation as quickly as possible. Now, if you look at this shape, you would want to move outwards from the origin, right? Because that if you move outward from the origin, you'd be ascending this three-dimensional function. So the gradient would point away from the origin, like so. It would point, or not, I shouldn't say origin, but away from the lowest point, so that we could ascend as quickly as possible. Now, if you're like, well, why perpendicular? Why couldn't it be like this, for example? Well, let me explain by looking at a ring that is, let's say, this green ring right here. Now, if I'm at this green ring, and if I move parallel, so imagine that we zoomed in on this curve right there. That curve, as you zoom in more and more, starts to look more and more straight, like a straight line. And that's called local linearity. And so if you were to move directly this way or directly this way, you would just be moving along the contour and you would have zero elevation change. If you moved sort of this way or this way, of course, you would be descending, you'd be moving downwards, you'd be moving to lower contours. And so that basically just says that we would want to move away from the origin, right? And so if we think about this green and this black, the blue and the green, and I ask myself, okay, what's the fastest way to ascend? Well, the fastest way to ascend would be the quickest way to get to the next contour, right? Because the next contour is sort of the next plotted elevation on here. And you could say, well, you could go this way. But notice that that vector is longer than the vector that just goes directly perpendicular to the surface or to the contour. And you can see that moving any other way, for example, this way, you can see that that's a much longer vector. It still gets me to the next contour, but it's not the fastest route. So the fastest route is just to move away from that contour as quickly as possible, and the way to do that is to be perpendicular to. Okay, now another thing to think about is what would the contour look like for our constraint? And this is the contour for our constraint right here, x plus y equals 30. Again, just those same rings plotted there. Well, x plus y equals 30, that's a function that has its own gradient, right? And so if this constraint, whichever of the contour rings it is tangent to, which in this case it's tangent to this red one, that means that the constraint is going to have, at that point right there, where they are tangent to one another, the constraint x plus y equals 30 will have a gradient that will point either this way or that will point this way, right? That would indicate that it is perpendicular to its contour. So it would move one of those two ways. So that's going to be the gradient of f. I'm sorry, the gradient of our constraint g. And then we'll also have the gradient of f, which I'll do in purple. And the gradient of f, well, we already know that it points this way. And I'm just going to offset those vectors to make it look like one's longer than the other, just so we can see that there are two vectors there. So a critical point for an objective function, given a constraint, occurs where the constraint function is tangent to of the objective function. Okay, so what we're saying here is that this is a critical point. And it's like, well, why is that a critical point? Well, we just established that the gradients either are a point in the same direction or exactly the opposite direction. But also one thing that we should note is if you are on this red contour, and if you were to move this way or this way, we've already established that that would keep you on that contour. You'd not change elevation. And what does it mean when our elevation doesn't change? Well, let's think back to two-dimensional functions. If I am here, then the slope is 0, and that indicates that if I move just slightly, my elevation should not change. So that would mean that we're either at a minimum, a maximum, potentially a saddle point, but if we just think about minimization and maximization, we must be at a critical point if slight movement in either of these two directions does not change the contour that we are on. Okay, so that, first of all, where this touches this contour is where the two functions have something in common, right? And not only that, but where they have something in common and they are tangent to one another, that means that movement slightly away from that point, but maintaining your position on f of x will not change your elevation, which means you're either at a minimum or maximum. Okay, let's put that all together. Fact 3, at the critical point, the gradient of the objective function is parallel to the gradient of the constraint function. So the gradient of the objective, let's write that, gradient of f is parallel to the gradient of g. Well, the way this is formulated right now, I would say that they are exactly the same, which certainly would mean that they're parallel, but the gradients could point in opposite directions. They're just parallel to one another. So if I take the vector, let's say 1, 1, compare that to the vector, let's say -2, -2, well, they have the same slope, and we can actually verify that -2, -2 is -2 times 1, 1. So to be parallel, you are a multiple of, and the multiplier that will apply, we'll just go ahead and put it on gradient of g. You could do this by saying -1/2 of this gives you 1, 1. But let's go ahead and put that multiplier here. And this just means is a multiple of the gradient of g. And so lambda, this symbol lambda, Greek symbol, is just some real number. So I'll just write it like this. It's just going to be some real number. Now, for a critical point to occur, then it follows from that logic that what we need to do is we need to figure out the value of that vector x that makes this equation true. And that's one way we could actually discover where that point is by solving this equation. But not only that, we also need to maintain that g of x is equal to 0. Okay, that's that our constraint is equal to 0. And I'll come back to this in a moment because our constraint is set equal to 30, but we can solve that really easily. Now, lambda is known as what we call a Lagrange multiplier. That's named after the mathematician. And rather than to have to formulate it as these two constraints or these two equations, we can bundle this down into one equation, which is absolutely equivalent mathematically. We can prove that. It can be reduced to the Lagrangian function, which notice that the n is what you would get if you moved things over here. subtracted lambda times gradient of g, and by setting each of its partials to 0. So you're going to have one partial for each input, and then one partial with respect to lambda. Notice that this is set equal to the 0 vector because, well, we could have more than one input, but there's only one lambda in this formulation right now. Okay, so let's go ahead and do this for our example. So our equation, our constrained optimization problem is to minimize this function with respect to that constraint. Now, what we're going to call g of x has to be set equal to 0. So if I rewrite this as x plus y and subtract the 30 over, well, now I have it set equal to 0. It's as easy as that. And this right here is what we're going to refer to as g of xy. And that's just our one constraint. We have one constraint. So what we need to do is we need to formulate the Lagrangian. The Lagrangian, and I'll just write those inputs instead of as a vector, as the scalars, and it's going to be f of xy minus lambda times g of xy, which will be x plus y minus 30. All right, now if I take the partials, I'll take the partial of f with respect to x. Okay, when we do that, we'll get 2x minus 2, and then over here, when we distribute that lambda, notice that this will be minus lambda x minus lambda y plus 30 lambda. And we're differentiating with respect to x, so we'll just get minus lambda. And we are going to set this equal to 0. Then we have the partial with respect to y, which will be 2y minus 10. Again, minus lambda, set equal to 0. Partial of L with respect to lambda, which all of this stuff will be 0. With respect to lambda, we'll just get minus x minus y, and then we'll get plus 30. Again, set this equal to 0. Now, if you notice, earlier I mentioned that the Lagrangian is equivalent to solving this system of two equations. Well, the first equation we built into the Lagrangian, so that's already there. But the second equation, g of x equals 0, well, notice that this is g of x equals 0. It is, if you multiply both sides by -1, you get exactly x plus y minus 30 equals 0. So the Lagrangian just condenses everything down into one equation. Now the next thing we would need to do is we would need to solve for x, y, and lambda. Okay, so that's what we would end up getting. Now we could do this via substitution. We could do it via elimination, since this is a system of linear equations. So we could say we have x, y, and lambda as our three input variables, and then move our constants to the other side and do a reduced row echelon form. And the values that we would get for this system is lambda equals 24, x equals 13, y equals 17. Now we're not going to go into, in this particular video, what lambda is, but it can be interpreted in the context of the problem. But basically we found a critical point at x, y equals 13 and 17. And so what we're claiming now is that, well, we're hoping that's a minimum. Right now I'm going to put that question mark. Is this a minimum? I mean, hopefully we didn't find a maximum, because just because we wanted to minimize something doesn't mean we did. We just found a critical point. Now, the way that you could verify this is by picking points that are very, very close to 13 and 17 that fall along x plus y equals 30. So maybe doing like x is 12.9 and then y is 17.1. That still adds up to 30, and then just checking that the value of the objective function, that associated cost is higher than when it's at 13, 17. So you can't just plug in any x and y. You want to you want to pick an x and y that's near this point. So if we think about in two-dimensional space, 13, 17 is, somewhere over here. And remember, it just needs to be that x plus y equals 30. So if you slightly decrease x to say, I'll make this look a little bit more dramatic here just to separate them out. But if you pick 12.9, which is slightly smaller than 13, but I guess, sorry, y would need to be 17.1, so it would need to be a little bit bigger. Let me do it on this side. If you picked 13.1, then y would have to be 16.9 so that they still add up to 30. So take this point, plug it in up here, and the cost should be bigger. And similarly, if you put this point over here, which will be the point 12, say 12.9, 17.1, and you plug that in here, you should also notice that the cost is bigger, so that what we could conclude is that the critical point, in fact, does resemble a minimum. Okay, that's the constrained optimization problem. Notice that we went from having this constraint to really just having to do the same process, essentially an unconstrained problem, right? When we built the Lagrangian, there's no constraint that's evident in this other than it's constructed with a constraint built in, but we solve it identically to how we would do an unconstrained optimization problem. Now notice that up here, when we said x plus y has to equal 30, that actually gave us a function, and we could only pick points along this boundary here, right? But in some cases, it might make more sense to say that the constraint is an inequality. And an inequality just means not necessarily equal to. So let's just say that we had x plus y is less than or equal to 30. Well, that means that not only will the points on that constraint work, but any point that represents the sum of those two being less than or equal to 30. In this case, that would be anywhere below this line, and in fact, even in the negative quadrants, but we're going to be constrained by x being greater than equal to 0 and y being greater than or equal to 0. So any point in that purple region would work. So, of course, the method of Lagrange multipliers, that will take care of the boundaries on x plus y equals 30. But how do we figure out if maybe the minimum rests somewhere in here? Well, let's come back here for a moment. And you can see, all right, so the positive plane, xy plane is in this region right here. And you can actually see that if I plot that constraint, that on that constraint, all the points are actually higher than points that would be somewhere in that first octant. Okay, and so that means that I can pick plenty of points that are on this surface that are less than 30, where x plus y is less than 30. It would be anywhere inside of this positive xy plane. And so, well, clearly there's a better solution than the one that we found using Lagrangian. Well, in that case, what you would do is you would, in unconstrained optimization, so you could do gradient descent, finding all critical points such that g of x is less than 0, right? So basically just do an unconstrained optimization problem, find the critical points, and then test all of those to see which ones satisfy g of x is less than 0. And that will take care of everything in the purple region. So the unconstrained optimization problem, I'll make it purple here, and then run the method of Lagrange multipliers. That will take care of everything that is on the black. To find critical points that fall on g of x equals 0, evaluate f at all such critical points and compare. So that would be the procedure if g of x was less than or equal to 0.